All right, today we want to, once again, like Monday, do two main kinds of examples, more examples with probability and also more examples with just volume in this case today. These are difficult things, so you really want to do your best to pay attention and really glean as much as you can from these examples. Let's actually start with a purely graphical example that was on your homework for today. It's problem number 4 if you want to look at it. What they told you to do in number 4 in section 8.7 is to draw a PDF, a probability density function, for a situation where you've got a small middle class and a large upper class and lower class, many rich people and many poor people. Draw a PDF, a probability density function, and a CDF, a cumulative distribution function in that situation. And you really need to understand the key principles here in order to do this. Start with the PDF. That's usually the easiest thing to draw first, based on the description. Your horizontal axis here, X, would represent the income in whatever units are appropriate. And then remember the key principle. PDF stands for probability density function. Where the graph is higher, that's where you're going to get more dense data, you might say, that this approximates. Remember, the key principle the book said was that the integral of the PDF over some interval from A to B gives you the fraction of the data in that interval. Or from a probability perspective, if you pick somebody at random in that interval, or somebody at random from the population, what is the chance that in this case their income is in that interval? So what that means is, because we have a lot of poor people and a lot of rich people, you want the PDF to be high in value when X is small and when X is large, and lower in value in the middle when you've got a small middle class. So something like this might be the initial drawing you might make. And that's probably fine if you drew that. It's not technically maybe as accurate as it could be, because there is going to be somebody in the population that has the highest income. So in reality, the graph probably does come back down about like that, perhaps. But if you didn't draw that part, it's probably okay. Okay, this part is somewhat optional right there. But it is going to be a piecewise function as well, just like the example was on Monday. When X is negative, there's nobody with a negative income. So the graph is at 0 over there. Now you might argue and say, well, don't some people have a negative net worth? And that is true if your debt exceeds your income, your assets. You might say, well, if your debt exceeds your assets, you actually have a negative net worth. But income implies money coming in. You can't have a negative amount of money coming in if you're only focused on the money coming in and not the money going out. So it's 0 over there, and it's also 0 over here past the person with the highest income. So there's a reasonable graph of the PDF. There is technically a jump discontinuity at 0. It goes from 0 up to here. Should I draw like an open circle up here and a closed circle down there, or what? It's not a big deal either way, because the key thing to focus on is the area under the graph. And 1 point missing from the graph won't affect the area. What is the corresponding CDF? PDF stands for probability density function, or just density function for short. CDF stands for cumulative distribution function. Don't say density there, say distribution function. It is an integral of the PDF. Said another way, the derivative of the CDF will be the PDF. It is accumulating probabilities. It's accumulating fraction of the population. At any given value of X, the output of the CDF tells you the percentage of the population below that value of X, below that income in this case. X is still income. That function can't possibly be going down. As the income goes up, the fraction of the population with an income less than the given number can't be going down. This function never decreases. It always is either constant or going up. Its derivative, again, is the PDF. The PDF is 0 over here when x is negative, so the CDF is also, well, has 0 slope, and in fact has 0 value as well, because nobody has less than 0 income. Once you get to 0, because of the jump discontinuity in the PDF, technically speaking, there's a lack of differentiability in the CDF there. And you go from having 0 slope to having some positive slope. The positive slope effectively equal to the value of the PDF right there. A fairly high value. But then as x increases, the PDF goes down. And that means the slope of this graph has to go down. It has to be concave down. Where the PDF is lowest, that's where the CDF is going to have the smallest slope. There's going to be an inflection point in the middle class. And then the PDF goes higher again, so then the slope of the CDF goes higher again. The CDF is concave down where the PDF is decreasing, and concave up where the PDF is increasing. And if you just drew it, say that far, that's probably fine for the homework. Technically speaking, if you did this, we'd want it to go back down in slope until we get to a slope of 0 once we get to that person with the highest income, and have a slope of 0 thereafter. And once you've gotten to that person with the highest income, right there, say, then you've got 100% of the population, and the value of the CDF is up at 1. Is that clear, the relationship there? That's the key things to think about as you try to do qualitative questions like that. Can I clarify anything? All right, what we want to do now is continue to emphasize these same themes, but now with some examples that have formulas that are common kinds of examples to deal with. And also, we're going to use Mathematica in ways that you should know how to use for the test, maybe for true, false, or multiple choice questions, getting the syntax right, and knowing what the code I'm about to show you does to simulate the theory. And that's a good idea for reasons I'll tell you about more on Friday. It's good to be able to do simulations of the theory. The first example we're going to look at is going to be what's called a uniform distribution. And you had some examples like this in the homework. On some interval here, now I could pick any interval that I want. That's finite at least. I'm going to pick a particular interval, let's say the interval from 0 to 10. So that's interval notation. What I'm hinting at here by saying uniform distribution is that the PDF graph, this is going to be the PDF, probability density function, when x is between 0 and 10, is going to be some constant positive value. Some horizontal line there, where the output is C, and you have to figure out C like you did in some homework problems. And how do you figure out C in this case? What would it be? Go ahead, Michael. 1/10, yeah. Why? Because one property that PDFs need to have is they need to include all the data, so to speak, the entire population, 100%, which without a percent sign you write is at number 1. Meaning the area under the graph of the PDF, which gives you all the data, must equal 1. We require the area under that graph, which is the area of a rectangle, to equal 1. 10 times C, base times height, must equal 1. So C must be 1/10, or 0.1. Technically speaking, the function is 0 elsewhere. And if I write its formula, I should really write it as a piecewise function. Little f of x, I'm going to call it little f and capital F today. We called it little p and capital P on Monday, is going to be my PDF here. It technically is a piecewise function. It's equal to 1/10 if x is between 0 and 10. And it's 0 elsewhere, 0 otherwise. Should I put strict inequalities here, strict less thans, or should I put less than or equal to's? It doesn't matter. I chose to put strict inequalities here, which technically means open circles there and there, but it's not a real big deal. Again, because those individual points won't affect the area under the graph. So it's not really a big deal. That's the PDF. What's the CDF? CDF, I guess I'm changing my color scheme from above. CDF is going to be the integral of the PDF. It's going to be a function whose derivative is the PDF. Moreover, we have to interpret it correctly as, once again, giving you the percentage of the population less than or equal to any given number, any given income in this case. Well, okay, if it was an income, let's not assume it's an income here. It can only stay constant or go up. It can't go down. In an abstract formula, I'll write it down here, capital F of x as an abstract formula, allowing for possibilities of negative values of x, which will not occur for this example, but could for some examples. You actually want to do an integral starting at minus infinity. In the abstract, you want it to be an improper integral whose upper limit is x. Once again, we encounter an integral where a variable is in the upper limit. I should use a different letter from my variable, my dummy variable here. I've used tau before. This time I'm going to change it for fun to a different Greek letter. My favorite Greek letter. If you make it slowly, it's very, very beautiful. It looks like this. Isn't that beautiful? And that is called the Greek letter xi. And that's how you say it. At least that's how I've been told. Xi. That's the Greek letter xi. But it's even more fun to give it a different name and just to call it squiggle instead of xi. Squiggle. F of squiggle, D squiggle. And it's also fun to call it squiggle because not only is it very pretty when you draw it slowly, but it's also fun to draw it fast. Squiggle, 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 because it doesn't look as pretty then, but it's fun to draw. That one's not too bad. Fast, squiggle. Okay, but if you draw it slowly, then it's prettier. And it does look like this. And its official name is xi, but I think for the rest of the class today, I'm going to call it squiggle, just for fun, right? Mathematicians, we have to humor ourselves like this to just keep going at it. No, we do enjoy doing the math too, but to tell you the truth, me personally, I also just love the symbols, right? I love having symbols all over my page and people are like, what in the world are you doing? You know, you can do that too. You can show your parents, look what I'm doing in math class. That's called squiggle. All right, well, for this example, this simplifies. For this example, I don't have to do an improper integral because the PDF is 0 when x is negative. So I don't have to think about negative values of x. I can start my integral at 0. Oh, there my squiggle was not so pretty. Oh, well. Which means, this is important, which means the value of the CDF at 0 is going to be 0 for this example. There's some other examples where it's not, but for this example, it is. Anytime your PDF starts positively, once x becomes 0 or positive, your CDF is going to go through the origin. And it's accumulating areas under this graph. It's going to be, this graph's a horizontal line. You're going to accumulate areas with a straight line. In fact, the slope of this straight line must be the value of C, must be 1/10. Slope of this equals 1/10. And it's going to go up to a value of 1 when x gets up to 10. These axes are not the same scale, obviously. Yeah, when x is negative, it's got to have a value of 0. And when x is bigger than 10, it's the integral of the entire PDF over the entire domain where it's positive. It equals 1. So the graph is horizontal again at 1 once you get to 10. And the formula for this then is 1/10 x if x is between 0 and 10. 0 if x is negative, say less than or equal to 0, and 1 if x is greater than or equal to 10. Right, and the integral of 1/10 is 1/10 x. And we want the value to go through 0, so the plus c would be plus 0 really for this part. F of squiggle equals 1/10 for squiggle between 0 and 10. And if x is between 0 and 10, then I'm integrating 1/10 d squiggle from 0 to x, and that'll be 1/10 squiggle evaluated from 0 to x. Okay, you don't have to write this down, but you'd be doing this kind of calculation to ultimately get to that if x is between 0 and 10. Maybe you do want to write that down. What's the purpose of all this? There's a multitude of purposes. One purpose is to find probabilities or percentages of the population in certain ranges. So for example, I could find the probability that x is between, for example, 2 and 7, symbolically often written like this, P of x being between 2 and 7, P standing for probability. You could also interpret it as percentage. It's the integral of the PDF from 2 to 7. I could use squiggle again. I'm going to go back to x. It doesn't matter. It's a definite integral. So it doesn't matter what variable I use. By the fundamental theorem of calculus, that's capital F of 7 minus capital F of 2. 7 and 2 are both between 0 and 10. I can use the 1/10 x formula. This becomes 7/10 minus 2/10 is 5/10, 1/2, or 0.5. Any of those answers is fine. A 1/2 chance of being between 2 and 7. And that should make intuitive sense because the distance between 2 and 7 is 5. The length of the entire interval is 10, and 5 is half of 10. The distribution is uniform. We should expect the probability to be the length of the interval divided by the length of the entire interval, 5 divided by 10 in this case. Yes, this can be interpreted as a probability. I randomly choose somebody from the population or something from the population, and I'm wondering what x is for that person or thing. The chances before I look, say at their income or something, is assessed by this probability of being like a flip of a coin, 50-50 chance that x is between 2 and 7. And yes, you can think of it in terms of also fraction or percentage of the population with x between 2 and 7. If x were an income, this would be a society where everybody's equal. It'd be like communism. Everybody income is between $0 and $10,000 or something. Okay. Of course, even with communism, you know it's a lie to say everybody has equal income. The people that are the politicians have much higher incomes in communist societies, and everybody else has a low income. What else can we do? We can find an average. What's the average value here? I hope it's intuitive that it should be 5. halfway between the extremes because the distribution is uniform. The mean, the average is the same thing as what's called the center of mass. If you imagined maybe the region under this graph to be, I don't know, a thin sheet of metal or something that was uniform in its density, its center of mass would be in the middle, 5. It's where it would balance if the x-axis were a seesaw, or teeter-totter if you prefer saying that. Where would that balance? Where to put the fulcrum to make it balance? Put it at the center of mass, 5. We should expect a mean average value of x to be 5, but what does it equal? How do you confirm that theoretically? In general, in the general case where x could be negative and maybe arbitrarily big negatively or arbitrarily big positively, you have to integrate from minus infinity to infinity, and that would be an improper integral. Not f of x, but x times f of x. I made a mistake there. X times f of x. I'm not going to explain this formula today. I thought I'd have time, but I won't have time. Hopefully on Friday I could explain this formula a little bit. The book does give an intuitive derivation of it. And we could ultimately give a physical derivation as well. It's related to something called the law of the lever, which is related to making things balance. Sort of a physical derivation of this formula. For this example, we can just integrate from 0 to 10 because that's where the PDF is positive, from 0 to 10. X times the PDF. And the PDF, when x is between 0 and 10, is 1/10. So this becomes 1/10 x. Now just do the integral. Get 1/20th x squared from 0 to 10. That'll be 10 squared over 20 minus 0 squared over 20. 10 squared is 100. Divide by 20, you do get 5, like predicted. You can also find medians, which are middle values. For symmetric distributions, the median is the same as the mean. It'll let you read about the median. I didn't have time for it with the first class, so I'm going to say I'm not going to have time for it with the second class here today. Maybe I'll talk about it on Friday, but I want to do some more examples. I also want to show you how to simulate this in Mathematica. And this is code that you should know how to use for the exam, meaning you need to know the right syntax and know what the code does. If I type random variate with a capital R and a capital V, showed you this before, this generates random numbers, but I can also specify what distribution these random numbers should have. And for this example, it's a uniform distribution. So then I type uniform distribution with a capital U and a capital D. And if I want the interval where the PDF is positive to be 0 to 10, I can put a 0 and a 10 in here inside curly braces like this, close off the square bracket, then put a comma, and then put the number of data points. Say I want 100 data points, put a comma 100, and then the end square brackets. So this will now generate 100 data points from a uniform distribution at random. There they are. There's 100 data points there. If I enter it again, it'll do a different simulation, different numbers. What's going on there? Why do we get different numbers? It's because it's a random simulation. It's simulating data from this distribution at random. Let me give the output of this a name. I'll call it data. Or maybe I should call it uniform data. Uniform data. Once I've done that, then the output is stored in this variable that I've called uniform data. Remember that a semicolon suppresses output. If I retype uniform data and re-enter that, I see it. It's also beneficial in this case, just like with function definitions, to use a colon equals, because that will allow me to redo the simulation every time I re-enter just this line. I don't have to re-enter that line every time. I can re-enter this line over and over and over again and get a bunch of different simulations. To see that this is truly uniform, I should make something called a histogram. And just this basic syntax will create a histogram of this, just like the population histogram in the book from Monday. Showing it's a bar chart. There it is. Showing you that for this particular run of 100 simulated data points, 24 of them were between 0 and 2. 20 were between 2 and 4. 13 between 4 and 6. 14 between 6 and 8, and 29 between 8 and 10. Not very uniform, you might say. Well, that's just because it's the nature of randomness. If I continue doing this over and over again, doing the simulations over and over again, sometimes it will be very uniform, like that's reasonably uniform. And sometimes it won't be, but there will be no clear pattern. That's pretty uniform. No clear pattern to this in the simulations. Sometimes it goes up and down, sometimes it goes down and up, sometimes it goes down the whole way. There's no real clear pattern. Overall, it's pretty uniform. And in fact, if I did say 1,000 data points, the histogram becomes finer and you might say more horizontal. And that was a theme on Monday. It's just because your histogram is not horizontal, say, doesn't mean you wouldn't want to model it with a horizontal line or horizontal PDF, which is what we're doing here. We can also compute the mean, the average. Now this is going to compute a mean of data, not a theoretical mean of a distribution like I just did here to get exactly 5, but an average of actual data where it's going to be adding the numbers up, all 100 numbers up, and dividing by 100. That's how you compute an arithmetic average. And what that means is, because it's simulated data, is we will not get exactly 5. But it should be close to 5. Yep. And if I continue re-entering it over and over again, I always get numbers fairly close to 5. Sometimes larger than 5, sometimes smaller than 5. But always pretty close to 5, because that's the theoretical mean from doing the integral. You might wonder whether the simulation's perfect. And in truth be told, no simulations are perfect. They're not truly random in the most abstract, pure sense. They are what's called pseudo-random. But you, in practice, can't tell the difference between truly random things and pseudo-random things anyway. So it's not a big deal. You might wonder, what is pseudo-random? In a nutshell, it's something that seems random even though it's really not. Let's do another example. This time, let's make the PDF be not a horizontal line, but some slanted line. Let's still make its value 0 when x is negative. Let's make it be some slanted line with a positive slope when x is between 0 and 10. And then 0 otherwise afterwards. How high does it go? What's C going to be here? Well, I want the area of this triangle to be 1. We want 1 to be the area of the triangle, which is 1/2 base times height. And that would imply C is 1/5. 0.2 for this example. Might make sense to call this a triangular distribution, and we certainly could, and Mathematica does it. In fact, we'll when we do the simulation for this example, we will use a command called triangular distribution. But we're interested in the same things. What's the CDF? How do you find probabilities? How do you compute the mean and the median? Before I compute the CDF, remember the interpretation of this probability density function, emphasis on the word density. This is going to model a situation where your population, or your simulated data for that matter, is denser where the graph is higher. The graph is higher when x is closer to 10 than when it is close to 0. So data from the population or simulated data should be more densely packed close to x equals 10 than it is to x equals 0. Probabilities are higher when we find areas close to x equals 10 than we find them close to x equals 0, at least if the interval that we're talking about has the same length. So for example, if I find the probability that x is between 2 and 7 for this example, 2 and 7, I should expect a number smaller than a half instead of equal to a half. We will do that, but let's find the CDF first. Let's first write a formula for the PDF. Once again, it's piecewise. You really can't avoid piecewise for most of these examples that we've done so far. What's the slope of this line? It's rise over run. The rise is 1/5, the run is 10. The slope is 1/50th, 0.02. So the formula when x is between 0 and 10 is going to be 1/50th times x. And again, it doesn't matter whether I use strict inequalities like this or non-strict. It doesn't matter whether I use less than versus less than or equal to. It's certainly 0 otherwise. As before, technically speaking, the CDF is the integral of the PDF in general from minus infinity to x. But once again, for this example, we can start the integral at 0 because the PDF is 0 when x is negative. We want to make x the upper limit, and we want to put the f of something d something, and we'll use squiggle again, f of squiggle d squiggle. Right? Using squiggles just for fun, okay? Just because I like it. I do want to use something different than x, though, because I want to emphasize the variable is up there. This will be a piecewise function too. If x is negative, I'm integrating little f over negative values. Well, if this were minus infinity to x and x is negative, I'm little f is 0 over here. I'm going to get 0. When x is bigger than 10, I've integrated the entire PDF where the PDF is positive. Area is 1. It's only when x is between 0 and 10 that's a bit more interesting. That's where I'm integrating effectively 1/50th squiggle, d squiggle. Let's do it as a side calculation here. If x is between 0 and 10, I'm integrating 1/50th squiggle, d squiggle, to get 1/100th squiggle squared. What fun. Squiggle squared. Squiggle goes from 0 to x, and that will give me 1/100th x squared minus 1/100th 0 squared. 0 squared 0, of course, and so it simplifies to just 1/100th x squared if x is between 0 and 10. And the graph of the CDF is going to be 0 over here, 1 up there, and the graph of a parabola in between. Like that. That'll be the CDF. Cumulative distribution function. Probability density function for the PDF, cumulative distribution function for the CDF. What is the probability that x is between 2 and 7? I said it should be less than half. Let's see if it is. Integrate the PDF from 2 to 7. I can go back to using x here if I like, or squiggle, it doesn't matter. That'll be capital F of 7 minus capital F of 2. 7 and 2 are both between 0 and 10, so I get 7 squared over 100 minus 2 squared over 100. And that's going to be 49 minus 4 over 100 is 45 over 100, or 9/20ths, which is the same as 0.45. Yeah, a little less than 0.5. What about the mean? Do you think it's going to be less than 5 or bigger than 5?
I think it's going to be bigger than 5.
You are correct. Have a reason? Maybe related to that?
Most of the data points are gathered. If you assume, it's the graph is density of data points, right? So
Mhm.
the more data points you get on the right side.
Yep, close to 10 and less close to 0. More data close to 10, less close to 0. More weight toward the larger values, so to speak. We should expect a mean bigger than 5. Let's compute it now. Mean of x. Mean is just a synonym for average. Integrate over the entire domain, not 2 to 7. In general, minus infinity to infinity. For this example, that'll be 0 to 10. For this example, you have to think about where your PDF is positive. X times f of x, not f of x itself. Integrating f of x itself gives you probabilities. Integrating x times f of x over the entire domain where f is positive gives you the mean. When x is between 0 and 10, f of x is 1/10 x. So this becomes integrating 1/10 x squared. And that'll give you 1/30th x cubed. X goes from 0 to 10. And I'm worried that I got a different answer in the first section here. Let me just check and see what I did here. Oh yeah, the formula for x, little f is different. It's not 1/10 x, it's 1/50th x. That's not 1/30th, that's a 1 over 150. So you're going to get 10 cubed over 150, which is 1,000 over 150, which is 100 over 15, which is 20/3. 6 2/3, which is 6.6 repeating. Any of these answers is fine. That's the theoretical mean. Oh, my writing is really slanted there. Does simulation match theory? Let's see. Instead of uniform data, I want triangular data, you might call it. Why? Because the graph of the PDF looked like a triangle. That's why. Triangular distribution, perhaps. And in fact, if you look it up in Mathematica, there is a triangular distribution instead of uniform distribution. However, the syntax of using triangular distribution is a little different. If it's what's called a symmetric triangular distribution, what that means is the graph of the triangle, the PDF, is symmetric. It looks more like this, like an isosceles triangle for the top, and the peak is in the middle. That's not what we have here. We have one where the peak is at the right endpoint. So that syntax is not going to work. Is there one that does? Yes, this one does. Triangular distribution with mode at C. What does mode represent? For statistics, it represents the most frequent value. In modeling with probability, it represents the highest point of the PDF. It occurs at x equals 10. The mode is 10. So that's what I want to use. Where'd my cursor go? I can't find it sometimes. There it is. I want to use this syntax right here. Put the min and max inside curly braces, separated by a comma, min and max being 0 and 10. And C is going to be the mode, which is 10, where the PDF has a highest value, a maximum. So all I need to do this is just put a comma 10 in there. Let's just do 100 data points first, and let's try to see the data points. So I will get rid of the colon here. There's 100 simulated data points. And if you glance over it, yeah, most of the numbers are 5, 6, 7, 8, 9. Very few that are 0, 1, 2, 3. If I make a histogram, not uniform data, but triangular data, it looks like a triangle. Let's do 1,000 data points to see it more clearly. Yep. And every time I re-enter this, it does a new simulation with 1,000 data points, gives me a new graph, but no matter which graph it is pretty triangular. And I could find the mean, a statistical mean, meaning it's going to add up the numbers and divide by how many there are. There's 1,000 numbers. Add up 1,000 numbers, divide by 1,000. It should be close to 6.67. Not too far. Re-enter it. Sometimes I'm above, sometimes I'm below. If I did 10,000 data points, I could be pretty confident it's going to be 6.6 something, I think. Yeah. Oh, there it's above. Sometimes still above 6.6 something. Okay. Dare I even do 100,000? I dare. Yeah, very close to 6.67. And it does it pretty fast, evidently. Doing 100,000 data points there. Of all 100,000 of them very quickly. That's pretty impressive. I don't want to push it. You could try on your own. By the way, if Mathematica ever stalls on you and it's not doing anything, well, you can always close it out, but you can always go to the evaluation and abort evaluation or quit the kernel, and that'll stop its evaluation if it's stuck and not, if it's running and not stopping.